Uh, Hello everybody. Today I want to look at how to evaluate the Gaussian integral, which is integral from 0 to infinity of e to the power of minus x squared, right? So this is the integral that we are asked to evaluate. That is called as eta. So this is the integral that we would like to evaluate. This looks like a very complicated and daunting integral to even begin with. So the question really is, where do we even begin, right? What do we do with this, right? See, one of the techniques of problem solving that is able to cut through various problems is to generalize a problem that you have at hand. So for example, maybe turning this integral of a single variable to a double integral of two variables, and you might say that that is just complicating this integral, right? So because if I want to turn this into, say, some integral which is a function of x and y, then I'm not really solving the problem. I'm just converting one difficult problem into another even more difficult problem, right? But the thing about generalizing in say generalizing a problem, say, to a different domain like we are trying to do here, is that once we generalize a problem, we are usually going to be able to do much more wider range of operations on a problem. And it might just be so that that extra degree of freedom is exactly what you need to cut away at your problem, right? So with that in mind, we would like to generalize our problem, and we like to look at a slightly different problem. Okay, so what we will do is, let's say we take we square this, right? If you square this integral, then we can again rewrite this as times the integral of 0 to infinity e to the power of minus x squared dx, right? Now we can always change one of the variables, and we'll just change one of the variables to y. Now what we can do is we can now because x and y are independent variables, we can take the functions inside, and then we get the following integral. So we are now getting the following integral. Now again, basically what we have done is we have converted this problem to a different problem. So we are evaluating eta squared. So the question is, can we evaluate this? So one of the things that might immediately jump out to you is that we have x squared plus y squared here. That looks like the equation of a circle, right? So it might be useful to exploit this symmetry here. So basically this what we want to do is we want to convert this integral in polar form. So if we do that, basically we know that in polar coordinates, if you compute the Jacobian out properly, you should get that dx dy is dr d theta, right? And basically x squared plus y squared can be replaced with r squared. So then our integral becomes from r squared times r dr d theta. The second question is, what will happen to the boundaries, right? So initially we had in xy space, basically x goes from 0 to infinity and y goes from 0 to infinity. So basically it is this first quadrant, right? In the r theta space, therefore, say this is r and theta. So basically theta would have to then go from 0 to pi by 2, while r will be ranging from 0 to infinity, right? So then we can write eta as integral from 0 to infinity, 0 to pi by 2, r e to the power of minus r squared dr d theta. So eta squared is just integral from 0 to infinity r e to the power of minus r square dr multiplied by integral of this. So this basically just becomes pi by 2, and this integral looks a lot like gamma function, but if you don't want to do it that way either, you can do the following thing. You can rewrite it as d of r squared by 2, right? Yeah, so then you get pi by 4 integral from 0 to infinity e to the power of minus r squared dr squared, right? So this just becomes so then this just becomes pi by 4, right, total, the entire expression. So this becomes 1. So now basically we have the value that eta squared is equals to pi by 4, which implies that eta is square root of pi by 4 or square root of pi by 2, which means that our original integral, which is from 0 to infinity of e to the power of minus x squared dx, is just square root of pi by 2. So there we have it. So the main lesson here is that oftentimes when we are given a complicated problem to solve, a good idea might be to generalize the problem, because once we generalize a problem, we are able to propel that problem into a space where a larger set of operations are available to us, and it might just be the case that these larger sets of operations and principles or whatever that might be in this more generalized domain, it might just be helpful to or useful to solve your problem. So generalizing a problem is not always making the problem more complicated. Oftentimes it's just about this accessing this larger space of possibility. So okay, thank you for listening.